Hey, what's up, guys? This is Jun here again. So today, let's take a look the last problem of this week's weekly contest. 1659. Maximize great happiness. This is a very interesting problem. Okay, so you're given like a four integers, like m and n, which is the size of this grid here, m by n grid, and then you have also an introverts count and extroverts count, which stands for there are like this many introverts people and this number of extroverts people. And then they ask you to decide how many people you want to live in the grid and assign each of them one grid cell. And note that you do not have to put all the people living in the grid. And there are some like rules to to place each person's into this grid. So every time when you place a person into the grid, there's a happiness you can get or you will lose. So the introverts people, for those introverts people, they like to be alone, right? They don't want to talk to other people. They want to enjoy their own time. That's why their happiness starts with 120 and lose 30 happiness for each neighbor because they hate neighbors. They want to be quiet. And on the other side, right, the extroverts persons they won't have more people around them. That's why they start with 40 because if it's by themselves, they will not be that happy, right? So, but they will gain 30 happiness for each neighbor for each of their neighbor. Okay, and the neighbors only live on the directly adjacent cell, basically up, down, and left and right. So, and it asks you to, to calculate the maximum possible happiness we can get by placing some of the introverts person or the extroverts person in the grid. So remember, you don't have to place all the people in it, right? Mm, cool. So and here are some examples, right? I mean examples ones here. So the maximum we can get is we place so we have one introvert person and two extroverts person. So we place this one introvert person on this place on the top left corner, and we place those two extroverts person together, right? So that's why we can have like 20 240 because this is 100, and by placing 60, right? We have 60, but by placing on the second 60, we have a 60 plus 20, and then we plus another 20 gain from the other neighbor, right? 20, which will be 100, right? So that's why 100 plus 120. Uh, I'm sorry, 40. Yeah, I'm sorry. So at the beginning they have 40. So here's also 40. That's why 100 plus 40 plus this plus 80, right, equals to 240. All right, cool. And here are some like other examples. I'll just skip them. So at the beginning, I spent a lot of time trying to find like the optimal strategy to put those peoples. Basically, I was trying like a greedy like solutions. I mean, I was like, okay, so it seems like if we have like a grid here, right? Oh, by the way, so the constraints here, right? So the grid is not that big, only the what? Only 5 by 5, right? So let's say we have some grid here. Because I was thinking maybe we can have find a optimal solutions by placing the by placing each introvert or extrovert persons one by one at probably something like if we place the introvert person on the corner first, right? If we place introvert person here, because here they will only have two possible neighbors. Maybe we put the second introvert person here, and then here, and then here, right? And then we place the extrovert persons right in the middle first. I mean, something like this, or and then we put it here, we put it here. Yeah, but I failed because I couldn't figure out a workable solutions for that because there are just like too many cases we need to consider in this case. And I know, I mean, and now we don't even know if this gradient approach even work or not. So then actually, so for this problem, it turns out that it will be more like a backtracking or like a DFS approach, you know. Basically, we just try at each of the cells, at each of the cell, we try th basically we have three options, right? We either don't place anything in these cells, or we place an introvert person, or we place an extrovert person, right? So one, not not placed, right? Two, introvert person. Three, extrovert person. So that this is the only three options we have for each of the cell, right? But and then how about how should we place the those peoples, right? I mean so we'll follow from top left to the bottom right sequence. Basically, we'll place this one first, and then this one, and then this one, this one, this one, this one, right? We'll just keep placing everything until we have finished traversing the entire 2D grid here. So, but the difficulty for this problem is that, or it's like a little bit tricky. Every time when we place like a cell here, let's say we place an introvert person here. Okay, so for the introvert person, I use I here. How can we calculate the happiness we are getting by placing an introvert person here or extrovert person? Either way, right? Since we are only placing the peoples by the sequence from top down and from left to right, then which means that anytime when we place a grid a new persons here, there will be no peoples on below him or on the right. So which means that we only need to consider the peoples on the left side and above him, right? But the problem is that the question is that how can we track those two persons, right? So it turns out that all we need to do is we just need to, let's say assuming we have like m by n grids here. So all we need to track is we just need to track the last n values, which means that I'll just you can remove this thing here. Assuming we have another column here. So it means that all we need to know is the last n values because this is the this part, right? As you guys can see, so this part is the visible values that we can see because all the others we don't care because the moment we're placing the persons right here, all we care is the uh, is the last is this value plus this value, right? Because with those two values we can calculate the happiness, right? We are getting by placing either an introvert person or extrovert person here. Okay, and assuming, right? Okay, so assuming we have finished placing an introvert persons here, right? What do we do? So to keep the last n values, I'm going to have a list here, right? So at the beginning, right? So the the uh the length is the same as n here. So at the beginning we have a empty, 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 and empty. So the moment we have placed an introvert persons here, I will just use the I'll just use the index of the column here. In this case, is 2, right? To update this one here. Before this one could be empty or could be an extrovert person here, right? But now we only need this one. We only need we have updated this this column with the with the new value here, right? That's why we have I here. And then after placing this one, we have value I at index 2 here. Now when we're moving to this location here, right? And we have a j here, right? So the j, we have like j minus 1 is I, which will be this one. And the value of the j will be the ones above him. That's how we get those two values for the current location. Basically, the j minus 1 and the j. J minus 1 is the left. It's a left value, and the j is what? Is the ones above him, up. So every time we just update this one array here, and then we keep going and going until we have reached the end. Yeah, and that's how we keep track of the what's for the current cell, what are the values on the left and above him. All right, cool. So with that being said, I think we can start coding. So this code will be a little long. Just stay with me. I'll try to finish it quickly. So, and then after figuring out how can we track the neighbors, and then the remaining part is the DP, right? So for the DP, what do we have? We have like the current position, right? And then we have the remaining introverts people, and have remaining extrovert persons, and then we have the last n values, right? Basically, those four states is our DP states. It means that at this location, right? Basically, at this location, I mean, since I'm using a position here because so that I can only use this one parameters to get the I and j. So it means that the DP is like this at this position with this remaining introvert person and with this many remaining extrovert person and with the last n values here, right? What are the maximum happiness we can get, right? So that's how I define this DP here. Because we need all those four numbers to uniquely identify our current state, right? That's why it's a little bit like you can call it either 4D or even 5D because here actually it's I and J, right? So and we have RIU. For this one, I'm going to use like this Python's way to help us to remember, do the memorization here. And okay, cool. So let's write our base case first. So the base case is that if the positions equal to m times n, right? So when the position it has moved to the end of the grid here, and then we simply return 0 because we know we will not get any happiness. Okay, and now the next one is get I and j. So the I and j actually, so for in this case we don't even need that the I here. All we need is the J, because we'll only use J to calculate to get our neighbors, right? So the J is what? J is the position, do a modular by n. That's gonna be the J, right? And now we have the answer, right? We have the answer equal to 0. And then the first one is not place any person, right? And the second one is place an introvert person, okay? And the third one is place an extrovert person, right? And then in the end, we simply return the answer, okay? And then here, our final call here is that we're starting from 0, and this is the place, the number of introverts person, an extrovert person. And here, since we will be using the DP to help us to memorize the states here, we cannot simply use the list here. So we have to use a tuple, because list is not hashable in Python. That's why we need to convert it to a tuple. And at the beginning, right, I'm counting of it equals to n here. So here, I mean, empty means there's nothing, there's no person living in this cell. So I means there's an introvert person, and E means there's an extrovert person. I just use this string to represent the state of the last n values. Okay. So that's that. Okay, so now not placing a person here. So not placing person, it's just what is the DP of, we'll just simply move the position by 1, right? Increase by 1, and then we have introverts and we have extroverts, right? But by not placing a persons here, we still need to update the last n values, right? Because it means that we need to update the j's element of this one to be the empty, because we're not placing anything here, right? So that's why I have to to update it, we have to convert it into a list, right? Because tuple is not immutable. So we have these things here. I'm just going to convert it into that, So, and I'll just also define an old values, because we'll be using the same list for introvert person, extrovert person. That's why there's like a backtracking idea here, right? So this is J, right? So okay, so that's the preparation here. So and now we have these things for the J's one, right? For the J's one, we'll be updating to empty. Okay, so I'll just put this list here so that you guys can still remember that. So let's say these are the areas, right? We have place already, and all we care is only one row, of the values, which is this one from here to here, right? That's all we care, and we are at this J here, so that's the J's column. And by not placing on persons here, basically after this one, after placing an empty string here, so the row will become to like this, right? Will become something like this, and the ith values for this last n values, sorry, the j's value for this last n values here will become empty, right? That's why I update this one and I do these things here, and I have to convert it back to the tuple, right? This one, and after this thing's done, don't forget to change it back to the old values, right? Because we'll need it for for introvert and extrovert person. Right, so that's that. All right, and now to place an introvert person, so first thing to check is if we have any introvert persons left, right? If we have, then first, right? First, let's try to get the happiness of get happiness, assuming we have this helper functions to help us get happiness by placing introvert persons here, right? And then again, we'll have this one here. Right? So now we're placing an introvert person at this location, and then we'll call this DP here with this pos plus one, and then with the introvert persons minus one. So right, because we have used one of the introvert persons, and then we have these things as well here. So again, revert it, right? So now for the actual persons, we can simply copy it and just do a little small modifications here, here, and then this is the E, right? Here, instead of decrease the introvert person, we decrease the extrovert person. Yeah, here it's optional. We don't have to revert it back because there's nothing after this, right? But I'll just leave it here. It won't hurt. Yeah. So and this is the main part of the DP, right? Basically, we just oh, sorry. The most important thing is here. Since we're getting the maximum, we have to compare it, right? With the current answer with the compare the current answer with the values coming from the DP. And here is what is the happiness, right? So we get this happiness and we plus that. Right, same thing here. Maximum of the answer, right? Happiness. This is also happiness. Plus that. Okay. I think for this part I think for most of you should be pretty straightforward, right? It means that that's basically one part of the DP, the top-down DP, right? We're trying to get the maximum possible grade happiness by comparing with the current answer, and with the current happiness we can get, and then what's the remaining parts. Okay. Let's see. What else? Um, Maybe I'll try to write out like a comments here. So this DP means that, starting from position to the end of the grid, the max happiness we can get. Right. So that's the definition of the DP with this introvert, extrovert, and the last n values. Right. All right. So the only thing left is this happiness helper functions here. Right. So like I said, let's say we're at here, okay, and then this is the J's column, right? Okay, so for the helper functions, get happiness, right? So the first things we need is the current column, right? And the second one is what is the type of the person. And the last one is the last n values. So that's only three parameters we will need. So depends on the type on above the current one, and on the left of the current one, we'll have a different formula. So I mean there are like a bunch of different ways of calculating this, but for me I just use the ones that is the most intuitive for me. Basically, I get the up one. The up one is the what? Last n values of the j, right? So because the current j's one is the ones ab above the current location, right? And then the left one is this. The left one is the last n values of the j minus one. But since we could have like out of the boundaries issues, that's why I do a simple check. If the j is greater than 0, we use that one. Otherwise empty. So empty just means there's nothing on the left side. Okay. And then, oh, sorry. So, and then let's see what else. So now I'm going to calculate the up difference. So the up difference means that, by placing the by placing this current by having a neighbor by having a neighbor, the person above us, how many happiness can we get or lose, right? So that's why depending on the type of the persons above us, for example, if it is I, it means that, if it's an introvert person above us, he will not he will become less happiness, which means we'll lose 30 happiness. Okay. And else if the persons above us is an actual person, it means that he will be happier, right? That's why the difference, it will be gaining 20 happiness. I mean, if there's nothing, if there's no one above us, so it will stay with the 0, right? So same thing for the left, right? I'll just copy and paste here. I know we have some redundant code here, but I didn't encapsulate everything, right? But I will just use this one. So for the left person, same thing, right? Now, oops, sorry. So now I also need to calculate the neighbors for the current I here, depending on if the up one, if there's anything living on the above us or on the left side. That's why I'm also calculating neighbors here. So if it's one if up else 0, one if left else 0, right? Basically, if up is not empty, it means that there's a person in there, right? That's why I increase by 1, otherwise 0. Same thing for the left. And finally, we are ready to calculate the final answer. So now we have answer here equals to 0, right? And depending on the current type, right? If it's an introvert person, it means that we start from 100, right? Will be 120, and then will be decrease 30 by the numbers of the neighbors, right? And then we plus the left difference and the right difference. Okay. Same thing for the type equals to E, right? Here we have now we have like we're starting from 40, right? And then we increase 20 with the multiplied by the number of neighbors, and we also append the left and sorry, not the left, the right up difference. Yeah, and then in the end we simply return the answer. Yep. So that's how we implement this helper functions here. And yeah, let's try to run the code, see what happens. Oh, yep. So I need to pass in the parameters here. So the type is I, and this is the last, right? So keep in mind here. So be careful. Don't use the updated value here. Use the last one. So the last n value, the original one. Same thing for this one. Instead, we have an E here, right? Cool. So Run the code. Cool. So the test case passed. Let's try to submit it. All right. So cool, it passed. Mm, yeah. So just to recap, right? What we have discussed here. So first, we were trying to use Grady, but unfortunately we couldn't find the optimal solutions by placing the persons at like a optimal strategy with the optimal strategy. So that's why we try to use a backtracking, right? Plus DP solutions, and to do that we have to identify the state of a DP first. So the way we're identifying the DP is that, of course, we need to have like the current location, which is the position, right? And then the second one and third one is all, of course, the remaining introvert persons and the extrovert persons. And the last one is is the trickiest one because we have to somehow track the left elements and the up elements. But we cannot simply use two elements to track that because we're moving, so it could be anything, right? From could be anything from 0 to n minus 1. That's why we decided to use like n size of list to track the previously the last n values we have seen so far. Because with that, all we need is we just need the last element and the first element to be the ones on the left and up on the above us. Okay. And after that, it's just like the general three options cases. First one is not placing any person. Second one is an introvert person and extrovert person. And then we implement these helper functions, right, to help us calculate the happiness by placing either introvert person or extrovert persons at the current location. Of course, by not placing any persons, there's no need to calculate happiness because we're not gaining or losing any happiness, right? Cool. All right, so last thing, how about time and space complexity, right? So for the top-down DP, right, the time complexity is it's the number of the states plus the time for each of the DP functions. So let's see the number of states here. So the number of states, first the position is m times n, right? And then we have introvert and extrovert persons, which is the how many is the I'll just use k, I think, right? Minimum of my m times n and 6. Okay, whatever it is, I'll just use k here. So that's why we have k times k. And then the last one is what? It's the last n values, which will be another n here, right? Because there we could have n values. Uh, Actually, that's n times. Uh, Actually, so at each of the bitwise here value, we'll have zero, right? We'll have zero. We have empty, I, and E. So here it's not this. It's like the 3 to the power of n here, right? Because I've yeah. So that's that. All right. So that's the time complexity, and then for each of the DP functions, right? For each of DP functions, we have three if else here, which is the constant value time, and for the the get happiness is also a constant because we don't have any for loop or anything, right? Yeah, so that's why the total time complexity is just this one. Yeah. Cool. And space complexity is the is also this one, the similar like this one, right? That's the number of states, right? Plus times this n here. I think for the space complexity, since we have like this array here, instead of the state here, we also need like times another n in the end because of this n length array. If we use like the bit mask, I believe you can also use bit mask to track the previously n state. In that case, you can just simply remove this n space in the end. But that's not a big change here. All right, cool guys. I think that's pretty much everything I want to talk about for this problem. It is really an interesting problem. I hope you guys enjoy watching the videos. All right, thank you so much, guys, for watching this video. Stay tuned. See you guys soon. Bye bye.